So welcome you all for the lecture. This today's lecture is on chemical potential and entropies, and we will also discuss here the partial molar quantities like partial molar free energy, partial molar volume, partial molar heat content and their significance. So if in here the overall outline of the lecture is, first of all, we will discuss about the basics of thermodynamics, because these all are thermodynamic properties, chemical potential, what is the entropies, and partial molar quantities, partial molar free energy, and partial molar volume and their significance. So in this lecture, we will discuss these entities or these quantities like partial molar quantities and what is their relevance and how does they are having significant role in thermodynamics function or thermodynamic proper reaction in the case of reactions. So here if you see the thermodynamics, as you know, it is used to determine the feasibility of the reaction, because whether the reaction will be feasible or not, so this study is carried out in thermodynamics. So that is whether the process is spontaneous or not will be decided. So here it is also used to predict the direction in which the process will be spontaneous. So sign of internal energy alone cannot determine the spontaneity of a reaction. The concept of entropy was also introduced in second law of thermodynamics. So all you might be know what is the law of second law. So that is based upon the entropy and concept of entropy. So whether a process will go spontaneously or not, then it is considered as, if it is going, then it will be said as irreversible process. So in your earlier classes you have idea about what is reversible and irreversible process. So for such process the entropy change of the universe is positive. So the change in entropy of universe is the sum of entropy change of the system and the surrounding. So total entropy change is their surroundings and this system. So that is represented as delta S system and delta S surrounding. So this overall entropy is depends upon that. So now entropy, you know, and that is, you also know what is the chemical potential, because that is one of the very important uh, you know so here enthalpy, entropy and Gibbs energy are molar quantity. It means moles per kilogram. So here it is represented by Gibbs free energy per mole unit. So chemical potential is represented by mu I equal to del G upon del Ni. So here, in other words, you can say the chemical potential is a measure of how much the free energy of a system change by del Gi with respect to if you add or remove a number of dN I particle. It means how many number of particles you are either removing or adding in the system. So that value will, chemical potential value will depends upon that. So for the particle species, while keeping the number of the other particle, and the temperature and pressure is also needs to be kept here to see whether how much temperature and pressure is there, so that if it is constant, then you can also easily calculate the chemical potential. So it is by the way of, if you're having the Gibbs free energy in a case of a numerical problem, so then you can easily calculate it by with the help of this expression. Now partial molar properties, because these are very important. So these are some of the thermodynamic properties. As you know, entropy, enthalpy, internal energy are known as extensive properties, because their value change by varying mass of the system. If you are changing the mass of the system, so their value is change, and their value will change by changing mass of the system. In many thermodynamic equation, the change of state was due to the variation of temperature and pressure only. So accordingly, it was assumed that in case of a closed system, there is no change in the mass of the system. So this is very important. While in case of an open system containing two or more components, the number of moles of a various component can also be changed. So in such case, extensive property must be function of number of moles of various components of a system in addition to temperature and pressure of the system. So it means how much the temperature and pressure is of that particular system is also very important. So that needs to be also keep in mind, and it is in case of the specific numericals or specific kind of problems, it has been given either if it is a constant, then it will be given as a constant. So now suppose the temperature of a system be like, just you can take it is like T, and pressure if it is P, and if suppose the number of moles, their corresponding number of moles is n1, n2, n3 or up to the j, means this is any number. So here then according to the property of x with respect to these all numbers, and temperature and pressure will be the function of its temperature and pressure as well as the number of the moles of various components. So this can be represented with the help of this equation, x equal to the function of temperature, pressure, and the number of the moles, which is represented here for assumed, as we assumed here, like n1, n2, n3 and up to nj. So this can be represented by this function. So here you can simplify it further. Suppose that then the total number of moles will be, that can be represented by capital N. So this could be the total number of the moles which we had taken in a sample for carrying out this expression. So this could be n1, n2, n3 as mentioned above. So these is up to nj. So thus change in property can be seen here when the temperature, pressure and the number of moles change will be can seen from dx equal to del x upon del t at constant pressure and number total mole. This n, capital N, is representing the total number of moles into dt. So here this is a differential. So del plus you have to take it once with respect to temperature and another with respect to pressure. So this, in case of pressure, this will be the equation will del x upon del p at constant temperature, pressure and mole, number of moles and delta p. So similarly del x upon over del ni in case of temperature, pressure and n, then the equation will be take this form. So further you can see del x upon del n2, likewise you can take the same up to the del or dni or dnj, here it is represented as. So whatever the number of these number of molecules, this will be proceeded according to that. So the final form you can write it like this way. So this quantity which is del x upon del ni dp, where ni, n2 up to nj is called partial molar property. So this kind of equation is, if you makes its differential form, then you will get the partial molar property, and this quantity is called as partial molar property of the jth component or up to the component. If it is like up to xi, then you can say it is also represented sometime as in a form of xi. Overall quantity can be represented like in this form. So now thus the partial molar property may be defined as a thermodynamic quantity which shows that an extensive property of the solution or a mixture change with the change in the molar composition of the solution, while keeping the temperature and pressure constant. It is partial derivative of the extensive property with respect to the amount of component of interest, means how much component is there. So each extensive property of a mixture has its corresponding partial molar property. So each of the mixture, because each of the mixture will have a different number of mole, you can say here in terms of moles. So obviously that will depends, the partial molar property will be according to that mixture. Thus for any composition, like say up to the ith component of a system, then the change will occur according to that. So the equation will take, like for partial molar Gibbs free energy will be represented here. You can see that can be represented by this equation, del G upon del Ni, partial molar Gibbs free energy. So these are the simplified form of that. So this can be represented by del G upon del Ni at constant temperature, pressure and mole of the mixture, mole of the component. So this can be also represented by Gi and bar, that's a sign. So partial molar quantity, uh, in case of partial molar internal energy, if you want to calculate, so that will be, the expression will del U upon del Ni Tp Ni N2 N3 upon equal to, it is also represented, you can say Ui. So another, which is partial molar enthalpy, that is enthalpy is represented by H, so that will be del H upon del Ni. So similarly you can see the expression for partial molar entropy and partial molar volume as well. So here for entropy you can say like del S upon del Ni, temperature, pressure, T, P, N1, N2, N3 up. So it is also partial molar entropy is also represented by, you have to make a bar sign above the SI. So similarly this is the designation for showing the equation. So partial molar volume can be represented similarly in the same way as you will mention for the other equation. So for the same way you can express this, and this can be also derived as the same we derived earlier. So here now the physical significance of partial molar quantities, because these quantities are having very important relevance and very relevant significance in terms of thermodynamics, in terms of physical. So here the quantity xi bar, which is represented there, represents the actual value of x per mole of the ith component of the system. So this value may be same or different from the actual molar value, which is represented, can be said as x star in the pure state. So these two values, like partial molar values and actual molar value, are same in the case of ideal system. So while in the case of non-ideal system, these two values are different because of the interaction between the constituents, like actual molar values get modified to partial molar values. So that's why this can be having a different, because if the actual value get modified with the partial molar values, so then this will change. So this partial molar value may not be same in throughout the whole solution, since the extent of interaction vary according to the amount of constituent in the system, because that will depends upon the type of constituent present in any system in which you want to check these their significance, the partial molar quantities and their significance if you want to check. So therefore the partial molar value is dependent on the composition of a system, because the each and every component it will depends, like we are taking the sample here in terms of mole. So different molar solution if it is, then it will also change accordingly. Now partial molar volume. So there are some of the other partial molar quantities like partial molar volume and their significance as well. So the partial molar volume of a substance like if you say it is like a ith component. Ith means here there are might be a number of component, so we had just put it like ith component. So in a mixture, because you cannot count how many component or how many number is there, so just for the assumption it is assumed as like ith component in a, for example, in a mixture of volume per mole of substance, like suppose 1 mole 2 mole of any substance you are taking and you want to analyze this thing. So if you want to make any expression, then how can we see it? So in case of ideal solution, the partial molar volume of the ith component will be equal to its molar volume in the pure state, whereas in case of non-ideal solution, the partial molar volume is the molar volume actually occupied by the substance in solution of non-composition. So here the partial molar volume of a constituent of mixture change with the composition. So this will change according to the composition as well. So as the partial molar volume is the actual molar volume of the component present in solution of non-composition, therefore the total volume of the solution will given by the expression V total equal to N1B1 plus N2V2. So here you can see there are, if they are having the different volume, then you have to take separately and then you have to add this. So this will be the partial molar volume of the constituent will be taken as separately. Like if suppose N1 type of how much, it means N1 type of some particular component which is we designated as N1, so their volume, and similarly for N2 type of another component and their volume has to be taken up, and once you will add this, so that this will makes the total volume of the mixture. So this needs to be, here you can see once you can write the free energy change by the, if suppose it is a very infinitesimally small amount, so that we represent at del G, or like del upon del G upon del T, because this del you can represent for their very small change with respect to the particular, you know, at delta at particular temperature, so with constant pressure and, you know, total number of moles. So here the expression which comes is will get, you know, del G upon del P in different function you can change it. So the overall dG will be addition of all these you know, expressions. So here mu1, mu2 and mu_j are the chemical potential of the corresponding constituent 1 and 2. So we can change this with respect to, you know, n1 n2 can be represent, which is represented here, this mu d n1 mu d n2, and this is you know, in are the chemical potential of the corresponding constituent. So assuming temperature and pressure to be constant, then free energy change will be represented or can be expressed in form of dg Tp equal to mu1 dn1 and mu2 dn2, and up to the species either I or J you can assume. So this will be the expression which will finally will come. So here partial molar, in case of partial molar Gibbs free energy, let's suppose the system has definite composition having molar component like 1 2 3 up to the J, as we already mentioned earlier. So here then the integrating equation we can write here, G at Tpn, Tp as usual meanings temperature, pressure and total mole, so will be the eta 1 mu1 plus n2, you can say n1 n2 like here, and mu1 mu2 will up to nj or mu_j. Thus by looking this equation you can say that we can define the chemical potential, and since it is as the contribution to the total free energy of the system by 1 mole of each component of the mixture while keeping the temperature and pressure constant. So the Gibbs free energy of the system is the sum of n mu terms for the individual constituent of the system. So here you have to see that this n and mu terms is not for you know, for the overall. You have to see here For each and every component you have to add these, and then up to the whatever the number, then this value will comes correct. Otherwise this cannot be taken as a whole number in case of if the mixture is having different constituent. So for different constituent of the molecules or any mixture or any chemical mixture, if you want to check their partial molar Gibbs free energy and partial molar volume and any other properties which is partial molar molar properties, so then you have to see by this way. So here the another which is very important is Gibbs equation. This equation is also very important to check the chemical potential and Gibbs free energy. So here you can say chemical potential is dependent on the composition of the system. To understand this, take a total differential of the equation like dg equal to mu1 dn1. Similarly, for the separate separate component of the mixture, you can say the equation is as usual we had already discussed. So here you can see here, so mu1 dn1 plus n1 d mu1. Similarly, you have to add for the another component, third component, fourth one onwards, and until it does not goes to the last component, so that we are representing here like assuming like J. So you have to express it. So separating the differential equation of chemical potential and differential of number of moles in moles terms, then you will get the equation which is represented like dg equal to mu1 dn1 mu2 dn2, and plus you will come with mu j dnj with respect to the individual species. That is written over in this form. So in this expression you can represent the each and every components. So this is further if we see this equation. So as you know, since at constant temperature pressure, the equation will take the shape. Here we are taking temperature and pressure as a constant. So dg will be mu1 dn1 plus mu2 dn2 plus mu j dnj. Therefore, this equation will further in a simplified, once you will simplify the equation, this will take the shape n1 d mu1 plus n2 d mu2 plus you have to go up to the j, up to the number imaginary, or you can assume the number which is up to j, so that is nj t mu j equal to 0. So it is concluded over here that at constant temperature as pressure, system has definite composition, means that is having a very definite composition with respect to each and every component. So that can be, we can express here summation of nj d mu j equal to constant or 0. So here you can say this equation is known as Gibbs equation. So the significance, it is having very much significance. This equation is that the chemical potential of one component of a mixture cannot change independently of the chemical potential of the other component. So it means this cannot change independently of the chemical potential of the other component. So independently they cannot change. So this is having a very great relevance with respect to the various properties which we had seen, partial molar properties or partial molar quantities. So Gibbs equation is also very important for the calculating these properties as well. So this overall lecture has been prepared by taking the help of number of online resources and number of books, and also this material is only for instruction purpose and only, and has not any commercial purpose. So here I thanks to all for watching this video and listening this video lectures. Thank you so much.